Alright guys, welcome to today's class. Let's get started with today's lesson, alright? And the homework. Problem 9. How many prime numbers satisfy square root of 300 is less than square root of x is less than square root of 700? Well, first off, as we know, we must find the squares that are nearest, that are less than 300 and 700 respectively. Alright? So what about, okay, let's start with 300. It's the easiest, right? Well, how do we do that? Well, it's obviously, if we do 16 times 16, if you think about it and you multiply all of these together, you get 256. Now, we want to think if we can add one more. If we add one more to 16, that would be 17, right? Now, what is 17 times 17? Well, that's 289, which is the least square, that is the greatest square that is below 300. So from here, we know that the boundaries must be 18, at least 18. So 18 is in the group, all right? So it's at least 18. And for 700, it's the similar approach. We also know that 26 is 626, if I'm correct, 676, I think. It's square root of 676 is less than square root of 700, which means that 26, if you do the math, 26 is the least number that's just that its square is less than 700. So it's also below 26. So then we found new boundaries for 26 and 18. So x is between these. Now we just want to find the number of numbers. Well, it's pretty obvious as 18, 19, 20. Find all the numbers, and then you've noticed that we want primes, all right? The only primes there is just 19 and 23. So there's only two primes. Right? Now let's move on to problem 10. How many ordered triples of primes ABC exist such that A plus B plus C is equal to 7? Let's guys over trying this question and tell me this through chat. All right, let's get started with this question. So it really is only one driblet of primes that work. The answer is just 2, 2, 3. And considering all of the possible orderings, that's just 3. Or C. All right? Problem 11. How many ordered pairs of primes A slash comma B satisfy A plus B is equal to 20? Let's go to this question and tell me answer through chat. All right, let's get started with this question. So basically, how am I supposed to approach this? Well, notice that, remember that the ordering is not the same. All right. So, for example, 3, 7 is not 7, 3 in this case. All right. So orderings do matter in this case, all right? So how many ordered pairs of primes a comma b satisfy a plus b equals 20? Well, we first find the prime pairs, all right? There's going to be 13 and 7. That's 1. And 7 and 13. I mean 7, I mean 17 and 3. These are the only ones, right? Remember that you can flip it over to become 7, 13 and 3, 17. So there's a total of two choices for the pairs and two ways to flip them. Since there's 13, 7, 13, so it's 17, 3 and 3, 17. That's a total of 4. So the answer to this question is just 4. Of course, if it's just pairs, not ordered, there's no order, it'll just be D. But in this case, it's going to be B because 13, 7 and 17, 3 can be each ordered into two ways. Alright? Now let's move on to problem 12. How many ordered triples of primes A, B, C exist such that A is less than or equal to B is less than or equal to C? It must follow this, right? And A plus B plus C is equal to 26. I'll let you guys have this question and tell me your answer through private chat. All right, let's get started with this question. How many ordered triples of primes A, comma B, comma C exist such that A is less than equal to B and is less than equal to C, and A plus B plus C is equal to 26. All right. How many ways are there to do this? Well, notice that three odds added up cannot be equal to an even number. So there must be only exactly one even and two odd. Right? And we can't have three evens since three evens, the only even prime is two, so two plus two plus two is just six, not 26. So we must have one to be two, which has to be A. A is just two. Now we want to find how many ways now we can make 24. Now it's just odd numbers, right? So one way to do this is 11, 13. What is the other way? Well, 7, 17. All right. And then we have one more. All right. Split it out. 11, 13, 2, 11, 13, 2, 7, 17. And the last way, I think there's another way, yeah. Should be 19, 5, 2. These are all the methods. All right. Now, this follows the ordering, and we have nothing the same. So, it must be that exact ordering. Since A is less than B is less than C, A is all 2, B is greater than A, so it can only be 11, 7, or 5, and 13, 17, 19 must be also C. So there's only a possibility only be C or three ways. Right? Let's move on to problem 13. If A plus B plus C is equal to 28 and A plus BC plus CA is equal to 185, where A, B, C are all prime numbers, find the greatest of the three prime. Alright? Let's go over trying this question in 10 minutes through chat. Similar question, but a bit of a different solving technique. All right, let's get started with this question. So, if A plus B plus C is equal to 20, and AB plus BC plus CA is equal to 135, find the greatest of the three prompts. Obviously, the first thing that comes up to mind is the same exact question, but with a different sum. Well, in this case, that was 26. This one's 28. All right. So one of them has to be 2. We can just let A go to 2. Okay. B plus C must be equal to 26. Now, how do we get that? Well, let's do guess and check. All right. So for B and C, we can notice that it can be B plus C equals 26. Let's get 2B plus BC plus 2C is equal to 185. All right. Well, how do we find a a combination? Well, the first thing that comes up to mind is 7 and 19. Okay, let's see. 3 and 23, that works. 5 and 21 does not work. 7 and 19 work. We also have 11 and 15 that doesn't work. So 13 and 13 does work. We have 17 and 9, which doesn't work, and 19. Yep. See, there are all the combinations, only 3 combinations. And obviously you can guess and check through this. But what you'll end up with is just 7 and 19 as B and C. Alright? So 19 in this case will be the greatest prime. Alright? It's just guess and check. Alright? If you find all the possible ways, guess and check through A, B, B, C, C, A, and summing up and make sure it's 185, and then you're done. Alright? So these were basically what the problems, the entire solve, how you solve it is just the same exact way as we solved the previous questions. Just guess and check and do casework. Alright? Now let's do problem 14. The sum of three prime numbers is 40. Find the largest possible product of the two of the three prime numbers. Alright? Let's go to try this question and tell me the answer through chat. All right, guys. Let's get started with this question. So basically, the same exact strat as we did before. All right. So it's two. As some of three prime numbers, it's gonna be two. All right. One of them is gonna be two, obviously, and the rest. And then we got 38. We got 38. Okay. Now we get two triples that are possible with prime numbers only. 1919 and 731. All right. These are the only two triplets we can get. And obviously, the greatest product is going to be the one with the closest numbers, all right? If they got the same sum, the greatest product is just the ones with the closest numbers, all right? So it's obviously going to be 19 and 19, which multiplied together just gives you E or 361, right? Now let's just move on to problem 15. How many ordered triplets of three prime numbers exist for which the sum of the numbers of the triple is 24? All together, let's try this question and tell me answer through chat. All right, guys, let's get started with the discussion. So, basically, an order triple of three-pound wrestlers exists as the members of the triple is 24. Remember that order does matter in this case, so we gotta account for the orders, all right? And notice that one of them must be two, as always. Okay, so it'll become two, and we're left with a 22. Now, the net other two-pound numbers must be summed into 22. So, how many ways are there to do this? Well, there's 11 and 11 works. 7 and 15 does not work. But 5 and 17 do work. Uh, 3 and 19 also work. And that's it. Right? So there's a total of 3 triplets. And this one has 6 ways. There's 3 choices to put in the first one. 2 choices means the second one, and one is just already guaranteed. Alright? So that would be 6 ways. Similarly, you can do this for 2, 5, and 17. That would be 6 also. And 2, 11, 11. Well, 11 and 11 are the same. So we got to divide by 2 to count considering them distinct. So there's going to be 6 divided by 2 or 3 ways. Adding this all up is 15. So the answer to this question is just B. Alright? Now let's move on to problem 16. If the sum or the square of a prime number and an odd positive integer is 125, find the odd positive integer. Let's guys want to try this question and determine answer through chat. Alright guys, let's get started with this question. So basically, the sum of the square prime number and the positive integer is 125. Well, the square of a prime number must be pretty close to 125, right? Because it has to be even. First thing that pops into my head is to notice that this must be even and odd, okay? So it cannot be very close, right? In most cases, it would be close if it's not, the other integer is not odd, right? In this case, it must be 2. 2 squared is just 4, and the odd positive integer must be 121. Alright? So the answer to this question is just A. Alright? Now let's move on to example 22. If A plus B plus C is equal to 68, and AB plus BC plus CA is equal to 1121, where A, B, C are all prime numbers, find the value of ABC. This basically has the same format as the problems we did before. So if you just did the problems we did before, it's just a little bit more computationally wise heavier. Like for example, like this question. Exactly like problem 13, but it's just more computation. Alright? Same exact thing, we just let A be 2. Simplify AB plus BC plus CA into 2B plus BC plus 2C equals 1121. Find all possible triplets of B and C, try them out, and may see if they work, and then voila, you're left with the answer. Alright? In this case, the ones that work is just notice that we want to just find BC, alright? Because we already know A. So that's where the key genius comes in, alright? Instead of case working, we can just notice that B plus C is equal to 66. Plugging that in, we get BC is equal to 989. Doing the multiplication, 2 times 989 is just 1978. Or B. Alright? Now let's move on to example 23. For how many positive integers A is A squared minus 3A plus 2 a prime number? I think we've went through this question before, haven't we? Yeah, I'm pretty sure we went this before in last class or something like that. So I'll skip this question for now. Alright? But the key idea is just using binomial theorem. Alright? And trinomial theorem. Now let's move on to example 24. Find a positive integer such that the sum of the positive integer and 72 is a square number, and the sum of the positive integer and 55 is also a square number. I'll ask you guys to try this question and tell me your answer through chat. All right, guys, let's get started with this question. So the square number is should be very close to each other. They are indeed very close to each other. So this number should be quite small, I would say. Quite small. First thing that pops up to my head is 9, alright? Since 9 plus 72 is equal to 81, alright? So I write this out on 55, and that is just equal to 64. And voila, our we found a number that satisfies both of the conditions. So it's just 9, alright? So this is just reasoning, alright? So how do I find that? Well, 72 must added to that number must be the square. But 55 added to that number is also a square. This is just telling you that that number must be very small in order for that to happen. So it must be B or 9. Alright? Now let's go on to example 25. For how many integers n is n squared minus 8n plus 15 a prime number? Well, the 25, example 25 and example 23 have very similar arguments, okay? So first off, you gotta learn factorization, right? There are many videos online that teaches you how to factorize a trinomial, alright? In this case, I'll just assume that you've learned it, alright? Or just use FOIL, okay? Well, notice that this factorization must be in form of n minus what? Times n minus something, alright? No. Notice that the product must be 15, alright? And the sum must be negative 8. Alright? Or in this case, if you just only consider this, it's just going to be 8, okay? So the sum of the numbers must be 8, and the product must be also 15. Only numbers that fit that description is just 3 and 5. So the factorization is just 3 and 5, alright? Notice that n must be greater than 5. So the only number that fits this, one of the numbers fits the description is just 6. 6 minus 3 is 3, 6 minus 5 is 1. Now we continue. If we plug in 7, 7 minus 5 is 2, and 7 minus 3 is 4. Notice that once you get n greater than 6, you only have composite numbers now. Since n minus 3 cannot be 1, nor can n minus 5. So the answer to this question is just 1 or B. Alright? Now let's move on to problem 17. For how many positive integers n is n squared minus 4n minus 21 a prime number? Same exact trick. This time, different factorization, alright? Assume that it's like this, n minus this times n minus this, alright? We don't need to know these numbers, but we do know that this number, these numbers, I'll just write question mark to not put any confusion. N minus question mark times n minus another question mark. I'll just say, let me just say x, okay. N minus x times n minus question mark. X and question mark must be multiplied to equal to 21, negative 21, okay? Alright. And x times plus question mark. Well, this is all negative, by the way. Negative x times negative question mark is just x times question mark. So it's negative x plus question mark is equal to negative 4. Alright? Or x plus question mark is equal to 4. Alright? So how do you approach this? Well, it's just system of equations, your classic approach, alright? So basically, coming from here, you just notice that, oh, so x times question mark must be negative 21. So one of them must be negative 7 and one of them must be 3, alright? Or 7 and negative 3. Clearly, x can be 7 and question mark can be negative 3. It doesn't matter which way we choose. Just they're basically the same. Plugging it in, that works. So x must be 7 and question mark must be negative 3, or vice versa. Now, for how many positive integers n is that a prime number? Well, n minus 7. times n minus 3. N plus 3. N minus 7, this number must be greater than 7, alright? Alright, so if we put in 8, we get 8 plus 3 equals 11. So we can get 1 times 11. What happens when it's less than 7, okay? What if we have negative numbers? These are both negative. Since we only want positive as the product, one of these must be negative, okay? Both of these must be negative, I mean. So that's only going to happen when n is less than negative 3. Less than negative 3, that's an equal to. I'll just write in this case. Or, and it follows that n must be less than equal to 7. Follows this constraint. Alright? So let's start with negative 3. Negative 3 plus 3 is just going to be 0, alright? So, up it up a notch. We can get negative 3, or it becomes negative 4 in this case. Negative 4 minus 7 is negative 11, and negative 4 plus 3 is negative 1. So that comes up to be exactly 11. So it goes with 1 and 2 possible ways. Well, after that, we can't do any much more since one of these numbers must be 1, and there's no way to do that. So the only possible ways is with negative 4 and 8. So the answer to the question is just B. Alright? Now let's finally go to problem 18. A group of 25 pennies is arranged into 3 piles such that each pile contains a different prime number of pennies. What is the greatest number of pennies possible in any of the 3 piles? Okay, so how do we approach this? Well, notice that one of them must be even again. Remember? So it must be 2xy. That is a total of 25 pennies. Alright? Similar acting as we do before, we just do casework. Well, we want the x to be as small as possible, or y as small. It doesn't matter. We just want to find one of the numbers to be the x or y minimized, right? Or the smallest number possible. So from here, you can clearly get from here, this becomes x plus, this becomes 3 and 22 doesn't work. 2 and 23 do work. But they're different, remember? So this must be, it could be 5, but 5 doesn't work because 5 divides 25, which means the rest is going to be a composite number. 6, 7, okay, it got 7. 7, 18 does not work. Oh wait, 7 and 16 does not work. If I'm correct. We want 23, alright? So, wait, did I do the math wrong? Yes, I did the math wrong. 5, 18, we do 19. Let's see. 19 to 23, that's gonna be 4. 17 and 23 is gonna be 6. 11 and 23, that'll be 12. And 15 and 23, that'll be 8. And 13, 23, that'll be 10. But I think this answer choice is not correct. Yup, answer choice is not correct. So, reality, this cannot happen. I'm pretty sure this cannot happen. Since we have 23, and this is double. So, one of them must be even. Oh yeah, I forgot. It must be all odd, okay? So, we just let 3, and we get 22. And obviously comes from here. It's just 19 and 3. So, there must be 19, alright? Remember, oh yeah, you can't have it. Okay, I'm at 17 and 5. 17 and 5 do work. Yeah, it's 17 and 5. So it becomes D or 17. Since we can't have this distinct and we have to have distinct also. And this has to be all odd because 3 odds added up must be equal to 25. That's the only way to possible. So the answer to this question is just 17 or D. Sorry for the slip up. Alright, that's it for today's class. I hope you guys have a wonderful weekend and I'll see you next week. Bye. And good luck on the AMC8s.